vector. It's just that, okay? It's nothing terribly exciting. Anyway, and here's like the method. We just transpose to swap rows to columns and construct the column space by taking spans of the columns. I think I need to show you an example. So this is pretty much the takeaway how to calculate things theorem here. Probably I need to show you an example of this. If I can do that, that would be awesome. Let's see here. Sorry. All right, let's look for something that's like, what example am I on? 9. All right. Oh, 5?
Oh, you're right, it's 6.
6? All right. So let us look at g of x, y, z, w equal to, oh, I don't know, x squared plus zw, comma, xy equal to, I don't know, 0.42. All right, great. So does that even make sense? What am I defining here? This would define a what? A surface, possibly, if I haven't made up bogus equations. We've got a 4-dimensional context. We've got 2 equations. So this describes a surface in R4. So in this context, my G prime at x, y, z, w is what? We've got 2x, y, partial y derivative, 0, x, right? Partial z derivative, we got ourselves a w. And we got what here? Thank you. And then the w derivative, and, oh, 0, okay. Great. Now, in order to calculate the tangent space and the normal space to a point, we need to find a point on this surface to study. So I need for you guys to find me a point in 4 dimensions which actually solves 0.42 like that. And I would also like a point at which this has rank 2. So I need 2 things. I want g of blah, 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 blah equals to 0.42, and I also need the rank of whatever this point is of g prime of p to be equal to 2. 6 and 7?
For x and y.
6 and 7?
36.
Does that work?
And then we'll do z is 36 and w is 1.
Well, you could also just use 0, 42, 0, 0.
No, we can stick with the 6 and 7, but if I want to make this work out to 0, I need to do what? That's 36?
Yeah, so you need -1 and 36.
-1 and 36?
Yeah.
Does that work? I think that works. I think that's fine. Let's go with that. That's our point P.
That should give us.
What's that?
That should give us what we want.
It's perfect? Okay. There it is. That's the point. All right. So what's g prime of p? At this point, that's my p. We got what? We got 12. We got a 7. 0. What's x? 6. My w? 36. Okay. 0. This is definitely rank 2. We're good.
Yeah.
Z. What was that, -1? Great. So the tangent space at P to S, it's got to be like P comma something. Well, it's two-dimensional, okay? It's two-dimensional. Get out of here. It's two-dimensional. So I'm going to write it as a span of two vectors. My point is there's a point of attachment P, and we'll figure out what goes here, okay? Point of attachment P, and we'll figure out what goes here, all right? I don't know what goes there yet. But whatever goes there, they have to be perpendicular, right? Whatever goes here, we call it V1 and V2. We need that V1 dotted with the vector 12, 0, 36, -1 has to be equal to 0. And we also need the V2 dotted with the vector 7, V1 and V2 both must satisfy the equations Vj dot this and Vj dot that is equal to 0. So how do you find a four-dimensional vector which is perpendicular to a given pair of, yeah?
You could append 0, 0, and then just
Are you just guessing the answer? What's that?
you can append 0, 0 to the and just
Yes, that's exactly the point. Is that this is the problem of like doing row reduction. So we got 12, 7, 0, 6, 36, 0, -1, 0. If I was smart, I would just pull out the website. All right, fine. So row 2, -1/7, row 1. 1/7? No. Worse, 1/12, row 1, right? Worse, 7/12, row 1. Ay. 12, 0, 36, -1. So if I take 7 minus 7/12 of 12, of course that's 7 minus 7, which is 0, was the whole point of doing this. The 6 is unmaligned.
Okay, it's just
36 to 30, it's 36 divided by 12 is 3. 3 times 7 is 21, so minus 21, I think. That was shockingly nice. And then, ew. I guess 7/12, right? This is actually enough. We can write the solution down from this already. All right. So so what this means is that 12, like, let me call these vectors A, B, C, D, just for the sake of not just to make my life easier. I'm going to call the vectors we're looking for A, B, C, D. So we see that A, B, C, D must satisfy the equation 12A equal to -36C plus D, and also 6B is equal to 21C minus 7/12 D, which tells me that my ABCD actually has -36C plus D, 21C minus 7/12 D, and C and D are what they are, so C and D. So you factor the C out, and you got yourself a -36, 21, 1, 0, and then D. We're going to factor out a D over 12 for the sake of common human decency. So D over 12, and that's just a trick, but that's going to give me a 12 minus 7, 0, and 12. If I did my job, the vectors that I give you at the bottom of the board here, this guy and that guy, are what I should be able to use for V1 and V2. Moment of truth. Is the dot product of V1 0 with those rows?
What happened to, if you're replacing the A and A,
It worked! What's that? Yeah.
what happened to the 12A? Because you said that was 12A, but then you replaced A, which you said was 12A.
Yeah. Oh, my celebration is short-lived.
Sorry.
Son of a gun.
Yeah, I get minus 575.
So I was supposed to take this divided by 12 and that divided by 6. Which gives me V is C times what? I have 36, so that's a, oh man,
What is it, 3?
3. It's a minus 3. 21 over 6, great. C is 1. 0. I guess I'll just factor D out since you guys did this to me. 1/12. 7 over 72. Happy? Happy? Let's see. 72. 0. And 1. Yeah, 1. Allegedly, those vectors should be perpendicular to the given vectors.
21 over 6 is 7.
What's that?
21 over 6 is 7.
I don't care. But yeah. So, all right. Listen, for those of you who've not had linear algebra yet, there is a simple website to do all this. We can just plug these numbers into a website and it will do the reduction and we can read off the solution. I'm sorry, I've made it ugly. But the method should be somewhat clear. We just calculate the Jacobian, put the point in question, evaluate at that point. That gives us vectors which are perpendicular. Now, there's an easier thing here. What's the normal space? I should have done this. What's the normal space at P to S? Well, that's just P comma the vector 12, 0, 36, minus 1, that one, and also 7, 6, 0, 0. See, these vectors span of that. These are the two vectors that are, whose span forms the normal space. There's actually a normal plane in 4 dimensions to the space at the point P. It's a surface, it's 2-dimensional, so there's 2 directions in 4 dimensions which are perpendicular to that direction. And those 2 directions are these, which are exactly the rows of the Jacobian. So that's one thing here. So help me if there's, oh look, I had an example. Son of a motherless goat. Let's see here. Yeah, son of a motherless goat. That's my go-to. It is now. So you can't question the questionless saying. So here is a level volume in 4 dimensions. This is a 3-dimensional set. The gradient to G is this. So the vectors which are tangent have to be perpendicular to this if we fix a point. So that gives me this equation, which actually just gives me this from arbitrary vector ABCD. So actually any vector ABCD which satisfies this equation is going to be in the tangent space at the point in question 2, 2, 1, 0 here. And so my tangent space is 3-dimensional because it's a volume, and the normal to that tangent space is particularly 4, 4, 4, minus 4, 1. That vector is perpendicular to any vector that satisfies this equation. And there happen to be 3, it's a 3-dimensional space. Now, so like here's one that was like the one we were just trying to do. I have from R4 to R2, here's the defining equations. I made up I like the point you guys made up. I really wanted that to work better. But this one here, the point in question, eventually I'll get it. 1, 1, 0, 1 that's my point P that I study. And I look and I find that the gradient to the first component of the first defining level component is this, and the gradient to the second level component is that. So to find vectors in the tangent space, I need vectors which are perpendicular to both of those, right? And I attach them to the point of attachment. So I have to look at these equations, gradient g1 dot that, gradient g2 dot that. So I've got these two equations, which, as you guys have pointed out, we can solve with row reductions in the most efficient, like solving with row reductions is the way to solve those elegantly, because it is this equation. So here's actually the linear algebra written out in a somewhat more cogent fashion. We're solving this equation, four unknowns, two equations. So if we do calculate the reduced echelon form of that matrix, you get this. And from that, you can read off the solution is as follows, which gives us, these are the two vectors, which if we attach to the point, that gives us the tangent space to this two-dimensional subset, two-dimensional space. Now, what's left over here is talking about the parametric viewpoint. All right, so I just want to tell you this before we leave today. If we want to look at, if we have a parametrized surface, the table, so here, let me just summarize. The level surface, finding the normal space is simple, because all we do is we look at the rows for the Jacobian of the defining level set, and those give you the directions for the normal space. Finding the tangent space is a little bit of a pain, because you have to like find the perpendicular to the normals to find the tangent space, which is a calculation we can do, but it can be tedious. On the other hand, if your space is defined parametrically, it turns out that the tangent space is super easy to find, but the normal space is a pain. And here's the theorem which basically says that if we have a parameterization, which I'm using an R for here apparently, as a k-dimensional patch, that's just another word for parameterization, the tangent space is simply attaching the column space of the Jacobian of the parameterization. So that's, in other words, you look at the Jacobian matrix of the patch and the columns of that, the column space of that attached to P gives you the tangent space. So what that means is if you want a basis for the tangent space, you can just select the pivot columns if you do the row reduction. In the normal space, on the other hand, you've got to calculate the null space to the perpendicular, null space of the transpose of that Jacobian. This is the calculation we were just doing. It's calculating the null space of the defining level map. But the tables turn if you have the parametrized set. The normal space is a pain to find, but the tangent space is easy to find. And like here's an example. If I have this surface in R3, R of xy is x comma y comma xy, which is to say z equals to xy in usual calculus 3 speak. Well, in this case, the Jacobian, this takes us back to the thing I wrote on the far board in terms of the regular surface, right? We're kind of in that world again here, but with x equals to u and y equals to v. And so here, if I have my Jacobian, I get this and that. If I pick a point, A, B, A, B in my surface, then the tangent space at P is simply the span of these two vectors putting in the point AB, which is 1, 0, B, 0, 1, A. So there you go, tangent space done. No further calculation. See how simple that is? Simple. On the other hand, to find the normal space, I have to find the vector which is perpendicular to both of these, which through a standard calculation is that. You can check that that works, right? This dot with that gives me 0. This dot with that gives me 0. And by the way, what's the other way we could find the perpendicular vector to a pair of three-dimensional vectors? Cross product, yeah. Is this easier than cross product? I think maybe. I don't know. If it's simple enough, you can guess them, right? So, I have more examples over here. Here's a surface in 4 dimensions. The calculation of the tangent space is still as easy as just differentiating and plugging in the point of attachment, which in this case I chose 1931. So I take that point and I attach to this with, s equals to, I've lost track. What was s equal to get here? 1 and s is 1 and t is 3 apparently. So put s equals to 1, that's why I got this. Put t equal to 3, that's why I got that. I don't know how I got that 3 there. That's kind of bogus, right? That should be a what? I don't think that should be a 3. That should be a what? I think that should be 0, 6, 1, 0 right there. That's a typo. And then to find the tangents, the normal space, I actually have to find the null space of this matrix, which the standard calculation is that. And so the normal space is these. Now, if it did this right, these vectors should be perpendicular to those vectors up here. But I have a suspicion they might not. I'm suspicious of this example. Okay, well, I'm still suspicious about that one. But anyway, I think that's, well, the double scrolling ended today's lecture. But I hope I've given you a significant vision of like how the next homework, like a lot of the next homework is finding tangent space and normal space to a given set. So I hope I showed you enough that you can get started on those. And I'll try to answer your questions about it next time if you got them. So.